Welcome to DP Tutorials by Don Jerwa. Now we will be highlighting on another topic from electrostatics, which is torque due to an electric dipole which is placed in uniform electric field. Now we have learned that when we have an electric dipole, there will be electric field associated with this electric dipole, and also some of the key features pertaining to an electric dipole is that when you have a system of a dipole, that means it is a system of two equal and unlike charges separated by a finite distance between them. Say, if I have a dipole in this form, and if I place one charge minus q and the other charge which is plus q, so there will be electric field lines associated with this dipole. Now we have also learned some of the key points, okay? Some of the key points that you need to understand about this topic is that we have also come across such equations about the definition of an electric field. Okay? Definition of the electric field is force per unit charge. Okay? Force per unit charge. And also when we learn with regards to an electric dipole, there is one factor, there is one term which we define as the electric dipole moment. Okay, the electric dipole moment. Now from here, the electric dipole moment is nothing but a vector quantity, and it is always directed from the negative charge, from this negative charge to the positive charge. So that is your electric dipole moment. Okay, that is your electric dipole moment. So these are the most important key features for remembering. Okay, for remembering how to derive this set of equation relating to the torque of an electric dipole. So let us now go deep into the details of this particular topic. Okay, so from here I have placed this dipole. Okay, I have placed this dipole in such a way that it is on the electric field. Okay, I have placed this dipole in the direction of the electric field line. So from all these white colored rays represents the electric field. Okay, represents the electric field. I will mark it by E, and all these electric field are uniform. Okay, I have also written over here that the electric field strength is what is uniform. Okay, and the strength of the electric field is capital E. So likewise, when you place this dipole on a uniform electric field, that means there will be some rotational force. When we talk about torque, okay, torque is nothing but a rotational force. Okay, torque is nothing but a rotational force. When we talk about torque, okay, torque is nothing but a rotational force. I will write in short as the rotational force, which makes certain bodies to rotate about a certain point. Now we already know that when we have a dipole, there will always be a center associated with the dipole. So if I mark this point, okay, if I mark this point, suppose let this be the point, okay, let this be the point O, okay, let that be the point O. That means O is the center of the dipole. At point A, we will place this negative charge, and at point B, we will place that positive charge. So with respect to point O, we expect that this dipole will rotate. Okay, so how will we rotate? How will it rotate? Okay? How will it rotate? So okay, let me write this direction of A. Okay, let me write this direction of A. Let me write this direction of A in the upper part so that it will be clear. Okay? So this is the direction of your electric field line in this direction. So likewise, we have also learned that the direction of the electric, we have to represent the direction of the electric dipole moment. the direction of the electric dipole moment represented by this vector p bar, okay, represented by this vector p bar, is always directed from the negative charge to the positive charge. So I will take this vector, and then this vector will represent what? The direction of what? The direction of your p bar, or your electric dipole moment. So now there will be force associated with these charges, plus q and minus q. So we will rewrite those equations pertaining to the forces. So for here, there will be force F1 acting on charge plus q, and there will be force F2 acting on charge minus q. So we have learned that the force, okay, experienced by the charge due when they are placed in an electric field is given by this equation. This is the key formula, F E equal F divided by Q. So F will be Q into E. So in this case, I will write F equal Q into E. Okay, F equal Q into E with the bar sign. And if you take the modulus of this, that means you'll get equation in this form, which is equal to F1 equal Q into E. Okay? F1 equal Q into E. And likewise, force on charge minus Q will be Q into E bar. If we take the modulus, okay, if we take the modulus, it means that this force F2 will be equal to Q into E. But these forces, we have, since force is a vector quantity, since force is a vector, all forces will be one vector in nature, both F1 and F2. So you have to represent them vectorially. So how will you represent them vectorially? For this charge minus Q, I will take this blue colored vector, and which means that this force on minus Q is F2. That means it will act in one direction. So let this be the force acting on the charge minus Q in the direction which is opposite to the field. Another vector representing force F1, that means it will act on this charge plus Q acting in the direction which is along the direction of what? Of the field lines. So let this vector represent that force on charge plus Q acting in the direction which is along the direction of the applied field. So let that be F1. This is the force. These forces, F1 and F2, okay, that forces F1 and F2 are acting in opposite direction. Okay, those forces F1 and F2 are acting in opposite direction. These forces F1 and F2 are acting in opposite direction. So such forces which act in opposite direction, they will constitute a torque, which means that if I have a body like this, and if I apply force in this direction, and if I apply force in this direction, that means this is F2, this is F1 at the center O, that means this body will what? This body will rotate. That body will rotate. So it will rotate about that point. Okay. So that type of rotational force is known as your torque. So from here, that means since these forces are oppositely directed, I have written over here very, very clearly that those forces are one. Forces F1 and F2 are one, are oppositely directed. Therefore, they will constitute one. Therefore, they will constitute the torque due to the dipole. So they will constitute torque. They will constitute a torque. So the definition of torque is that torque is either force into perpendicular distance. So from here, how to find the perpendicular distance between the force? Okay. So from this same diagram only, if we want to find the perpendicular distance, this is the dipole, and this is the force F2, and this is the force. This is the force F1. So what is the perpendicular distance between the force? When I talk about perpendicular distance between the force, that means this direction is that perpendicular distance. Okay, this direction is that perpendicular distance. So if I name this, suppose as point A, B, and C. BC, this BC is what is known as your perpendicular distance. Okay? That BC is what is known as your perpendicular distance. So why is it perpendicular distance? The thing is because the angle between the force F1 and F2 are perpendicular to each other. Okay? Even if you try to construct from here, that means this BC is perpendicular. This BC is your perpendicular distance. So that is the meaning. So from here, how will you find the perpendicular distance between F1 and F2? That means you have to drop the perpendicular. So from here, let me try to complete this diagram, bringing this portion over here and bringing this portion over here. That means what do you get? You get a right angle triangle. From this right angle triangle, it is evident that this part, okay, it is evident that that part is how much? That part, this angle, I mean, it is equal to 90 degree. So when that angle is equal to 90 degree, that means you can find the perpendicular distance. What is the perpendicular distance? This line will be the perpendicular distance, or in this case, BC is our perpendicular distance. Okay. So that is the figure. We have to find either force. Either force will be F1 or F2, and perpendicular distance. What is the perpendicular distance in this case? From the figure, the perpendicular distance is what? The perpendicular distance is that length BC. Okay, is that length BC. So either force, since these forces are equal in magnitude, F1 also equal to QE, F2 also equal to QE, F1 also equal to QE. So over here, either force will be equal to what? I will write Q, okay, into perpendicular distance. What is the perpendicular distance in this case? The perpendicular distance is your length BC. So you have to find that length BC. How will you find length BC? So from here, let me make another assumption. Let the direction, okay, let the direction with which the direction of the dipole moment P makes with the angle EB theta. So if this is theta, it implies that this angle also will be equal to how much? This angle also will be equal to theta. So from this right angle triangle, if you want to find this length BC, you have to use sine of the angle. Sine corresponds to what? What is the perpendicular? This BC in this case will be what? Will be our perpendicular, and this AC in this case will be our base, and this AB, okay, that AB in that case will be what? Will be your hypotenuse. Okay, it will be your hypotenuse. So those are the things that you need to learn. We will not write all those things. So you need. I'm just highlighting you. So from here, sine of the angle theta will be 1. Perpendicular. What is the perpendicular from the figure? The perpendicular from the figure will be what? Will be BC. Some people have, okay, perpendicular by hypotenuse. Hypotenuse is length AB. Okay. So from here, very clear that you have to find BC. Your objective is to find one. Your objective is to find BC. So BC will be equal to AB times 1 sine theta. You have to cross multiply this AB to the left hand side. So what is the length AB? The length AB will be equal to what? Twice A. So we will use this. On equation 1. Then we will rewrite the reduced equation. So tau represented by tau. Okay, we pronounce this as T A U. It is the Greek letter tau. Okay, so tau is your tau. Then so this will be from equation 1. This will be from equation 1. Okay, this will be from equation 1. Therefore, 1 implies QA. So what is BC? BC will be twice A sine of 1. Twice A sine of theta. So we have also learned that the electric dipole moment P is equal to the product of the charge and the dipole length. So from here, it is very evident that this factor, yeah, it is very evident that factor Q and 2A is nothing but what? It's nothing but this dipole moment P. So we can rewrite that equation. Okay, we can rewrite this equation. Q dot twice A E sine of theta. So what is that equation? Okay, what is that equation? This will be equal to P E sine of theta. This is the value of what? This is the value of your tau. Tau equal PE. So this is denoted. This is what is known as your scalar form. Okay? Scalar form of tau or scalar form of tau. We can also rewrite this in terms of its what? In terms of its corresponding vector form. We know that this resembles our dot product formula. We know that A dot B will be what? If no, not A dot B, A cross B. It is the cross product of two vectors. A cross B will be A B sine of what? Sine of theta. So from here, using that concept, that means we can write tau equal what? Equal B cross E. It is the vector product. So torque is a rotational force. Okay, torque is a rotational force. So this is the reduced equation. Tau equal P cross E. So there are two forms. Okay, this is what we write torque in terms of what? Torque in terms of vector form. Okay, torque in terms of vector form. So there are two formulas that you need to remember. Okay, tau equal PE sine of theta. Remember that this equation will be used for solving numerical problems. Also, tau in terms of vector form. When we talk about vector form, write the vector sign. So it will be P cross E. P cross E. So what is the physical significance? Okay, what is the physical significance? Say over here, if I have this one, if I have that vector, suppose from here, if I consider vector representing your if I consider a vector, if I consider an electric dipole, and from here we know that this is charge minus q, we know that this is charge plus q, and there will be your your dipole moment. And with the, if we represent this in terms, and these will be these will be your direction of your electric field lines. So how will you represent this vectorially? Okay, how will you represent that vectorially? Only in terms of your dipole moment. This is the dipole moment. The dipole moment is acting on this direction. This is the dipole moment vector. Then look at this E. Okay, we have the electric field vector. Okay, the electric field vector. So we will consider the dipole moment vector as the first vector. We'll consider this electric field moment, this electric field vector as the second vector. So this is the angle theta between the first and the second. So there will be there will be rotational force which is perpendicular. Okay, so this rotational force will be your torque. It will rotate, okay, in this direction. So since it is rotation from first vector to second vector, so this rotation will be in the anti-clock, in the clockwise direction. Okay, it will be in the clockwise direction. Okay, it should be in the clockwise direction. If you use your left hand rule, okay, if you use your left hand rule, that means over here we have these fingers. Okay, we have these fingers, and these fingers will point in the direction of P. And then also when you move these fingers in the direction of in the direction of E, that outstretched thumb, okay, that outstretched thumb will point towards you. That outstretched thumb will point towards you. So when this thumb is pointing towards you, so it means that the rotation is in the anti-clockwise direction, in the perpendicular to the plane of the page. Okay, perpendicular to the plane of the page. So these are the main important features. Why we discuss about this? Because torque is nothing but what? Torque is nothing but a vector quantity. Okay, vector quantity. It relates to rotational vectors. Okay, rotational vectors. So from here, we will learn some special cases. Okay, some special cases. So some of the special case from here is that when theta is equal to 0. How is it possible that theta will be equal to 0? Theta will be equal to 0. Okay, theta will be equal to 0 provided if this vector p, okay, if this vector p falls very close to 1, falls very close to the electric field vector. So how is that possible? So from here we know, okay, from here we know that if this is charge minus q, okay, if this is charge minus q and if this is charge plus q, so the electric dipole moment will be in what? Will be in the direction from P to E. And all these curves will represent what? Will represent the direction of E bar. So from this figure, it is very clear. From this figure, it is very clear that direction of P, okay, and direction of what? Direction of E are in what? Are in the same direction. So when these are in the same direction, which means that theta in this case is how much? Theta in this case is 0. So when you incorporate that, so we will find out how much is the torque. Okay, how much is the torque? So the value of torque, if you put on this equation, PE, and this will be sine of 1, sine of 0 degree. So you already know that sine of 0 degree will be equal to 0. So you'll have PE into 0, sine of 0, the value sine of 0 degree is equal to 0. So you'll get, finally, okay, you'll get torque to be equal to 1, torque to be equal to 0. What is the uniqueness of this equation? The uniqueness of this equation is that it tells us that the electric dipole, okay, that the electric dipole is what we describe as stable, okay, equilibrium position, which means that it will not rotate. Okay, stable equilibrium position, stable equilibrium position. When it is in stable equilibrium position, for this case, when theta is equal to 0, that means that there will be no rotation. The dipole will not rotate at all. Okay, so it is also known as the minimum condition. Okay, it is also known as the minimum condition. Very, very important. These should be known. Okay, this will be important for multiple choice question. Now next, when theta is equal to 90 degree, how will you find out that theta is equal to 90 degrees? So from here, okay, from here, the next diagram, suppose this is the minus charge and this is your plus charge, so the electric dipole moment will always be from negative to positive, so we will write this as P, and all these will be the direction of E. So if we draw only the vectors itself, so this will be one, this will be your electric field vector, all these will be electric field vector, and from here this will be one, this will be your electric dipole moment vector. So from this case, it is very, very clear that the angle between these two will be 90 degrees. So when this is 90 degrees, so the torque in this case will be 1. The torque in this case will be in that direction. Always rotation from the first vector to the 1, to the 1, to the second vector. So it will rotate in this direction, anti-clockwise and out of the page. Okay, out of the page. So from here, when you put this on that equation, or on this equation, we will have, okay, we will have torque is equal to PE. Then over here you'll have to write what? Sine. What is the value of the angle? The angle, this angle theta will be how much? That angle theta will be equal to 90 degree. So sine of 90 degree is how much? Sine of 90 degree will be equal to simply the value of 1. So PE into 1 will give you the value of simply PE. So in this case, the torque of the dipole when it is perpendicular, that means it will be maximum. Okay? The torque when the dipole is perpendicular to the direction of the electric field, when the dipole is perpendicular to the direction of your electric field, what will happen? The force, the rotational force will be maximum. The rotational force will be maximum. So in order to get maximum torque, maximum tau will be possible only, maximum torque will be possible only, maximum torque will be possible only if theta is equal to how much? Theta is equal to 90 degree. Next we will learn about what happens when theta is equal to 180 degree. Always remember that when we talk about the electric dipole moment, so in this case we will we will not write here minus charge. Okay, this is minus charge and this is plus charge. If this is minus charge and this is plus charge, that means electric dipole moment will be in this direction. So theta will be how much? Theta will be equal to 0 degree. But if you want to get 180 degree, that means you have to rewrite. Okay, this will be 1. This will be your, over here this will be a minus charge, and over here this will be your plus charge. And in this case that means your direction of your dipole moment will be from negative charge to positive charge. So this is the direction of your, that is your direction of P. This is your direction of your P vector. So in this case, what will happen? In this case, your angle will be how much? Our angle will be equal to 180 degree. Let us reproduce. So this is the direction of E. Yeah, all these vectors will be your E vector. Then how will you find out this electric dipole moment? The electric dipole moment vector will be what? The electric dipole moment vector will be this vector. Okay, this vector acting in the opposite direction, which means that the angle between them is equal to how much? 90 degree. Okay, the angle between them is equal to 90 degree, or 180 degree. I mean 180 degree. So from here, this is one. This is your electric field vector, and we have another vector which is your dipole moment vector. This dipole moment vector will act on this direction. Why? Because they are oppositely directed. So this angle over here will be how much? That angle over there will be 180 degree. Okay, 180 degree. So when you solve, put on that equation, tau will be equal to PE. Then you have 1 sine of 180 degree. So over here, sine of 180 degree also will be equal to 0. So this torque also will be equal to 1. This torque also will be equal to 0. But it will not rotate. But there is one important conclusion from here. The analysis, the physical significance. The physical significance of this is that the physical significance of this is that the dipole will be in the position which is unstable. Okay, unstable equilibrium. We define this as unstable equilibrium position. Okay, unstable equilibrium position. Unstable equilibrium position. Okay, so when theta equal to 180 degree, torque will be equal to 0, and when torque is equal to 0, there will be no rotation. The dipole is said to be in an unstable equilibrium position. So all these three special cases, 1, 2, and 3, okay, and this 3 are very important from examination point of view. Go through the lecture so that you will understand the concepts. Thank you.